You are listening to an American Free Press podcast. Joining me on the line is Dr. Daniel Bendor, a postdoctoral researcher in neuroscience at Massachusetts Institute of Technology's Picower Institute for Learning and Memory's Wilson Lab. Dr. Bendor, thanks for joining us today.
Dave, thanks for having me on the show.
Dr. Bendor, is it okay if I call you Dan?
Sure.
Okay. Dan, I saw a couple of days ago an article online, Researchers Successfully Manipulate Rat Dreams. I want to talk about that in a minute, but before we do, for the benefit of the listeners, can you give them a little bit of background about who you are and what you do?
Sure, Dave. I'm a researcher here at MIT, and in the lab of Matt Wilson, we're studying how memories get stored in the brain. And we focus on a particular phenomena called replay. So let me just describe what replay is. Imagine you go through your day, you're drinking coffee, we're having this conversation, walking around your house. In the hippocampus, all this information is getting stored in this brain region, and different patterns of activity are happening for each experience that occurs. When you go to sleep, it turns out that this brain region replays all these experiences. So you see the same pattern of neural activity occurring again and again and again. You have two stages of sleep, REM sleep and non-REM sleep, and it happens in different ways, but it happens in both. It's thought that this replay is actually your hippocampus talking to other parts of your brain. So there's this communication going on during sleep that allows information stored during the day in the hippocampus to be backed up to other parts of the brain. So it's just like your computer is backing up information once you put it in sleep mode. So we're trying to study these replay events during sleep to understand how memories get stored and backed up in your brain.
It's really cool stuff.
Yeah. We're really interested in what's happening at the level of individual brain cells. It's like if you were studying how a computer works, you'd want to know what's happening at the level of the transistors. So we have a technique in the lab where we can record many brain cells or neurons, their activity while the animal is running around and sleeping. So we just implant small wires in the brains of rats where they can just do what they do normally, and we record all the activity. So we can see patterns of activity when they do particular things. So in the region we're recording from, neurons over there act like a GPS system. So each neuron has a favorite location in the room. So let's say the rat is in the right corner of the room. One neuron will be very active and we'll hear on the audio monitor a sound like that. As the animal moves to another part of the room, that neuron will go silent, but another neuron will become active. So if we record activity from many neurons, we can interpret where the animal is in the room. It's almost like looking at the Matrix and you see all these weird symbols and you say, oh, this person is thinking this. Well, we can actually predict where the rat is in the room based on the activity of all these neurons.
Wow.
And if we train the animal to run back and forth, let's say on a linear track, so we get a particular pattern of neural activity, when the animal sleeps, we see that same neural pattern repeat again and again. So it's replaying, running back and forth on a track. This is how we infer what the rat might be dreaming about.
Right. The report, is that what you would call it, a report, or what do you call it, an article?
Article.
Okay. It actually said it looks like it was received in April, is that right? And accepted in August and published in September, is that correct? It takes that long to actually get published?
Oh, it can take much longer.
Really?
Depends on the review process. Yeah, because you send the paper in and you get blind reviews and you can go multiple rounds depending on what the reviewers ask for.
Did you start this year or last year?
Say about 3 years ago.
Wow. Okay, I didn't read that anywhere. In any of the articles I saw. Wow, okay.
There's some projects that take 5-6 years, yeah.
Amazing. 3 years ago, and now it's just being published. The article is about 8 pages long, and I highlighted a couple of things. And, of course, you mentioned the hippocampus. Did I say it right?
Hippocampus, yeah.
Hippocampus. So the O is kind of like not emphasized. So the hippocampus, which is a little part of the brain. Now, is the hippocampus, it's in all mammals then?
Yeah, it's in all mammals. I don't know if you're familiar with the movie Memento, but
Yes.
The character in that movie, he damages his hippocampus. And what happens is that he only has memory for about 20-30 seconds or till he's distracted, and then he doesn't remember anything that's happened.
Right, I remember that.
He remembers everything from before the accident. That's actually loosely based on a true story that someone had their hippocampus removed because of epilepsy. And he had exactly the same condition, that he could remember stuff from before the surgery, but not after. He only remembered for about 20-30 seconds, and then he would introduce himself again and not know who you are. That was evidence that hippocampus is important for storing short-term memories, but longer memories have been backed up to other brain areas, and so you don't need the hippocampus anymore to remember them.
Okay. And in here, in the paper, the first page says the mechanisms underlying memory consolidation are poorly understood. So still we know very little about this.
Right, and this memory consolidation is this backing up short-term memories to some other area for long-term storage, so you have a more robust memory storage in the brain.
Okay. So what you did was you used 4 rats, and they're called Long Evans rats. What type of rats are they?
It's a laboratory rat that's black and white. There are a couple different species we use that I think maybe a smarter version.
I gotcha. Maybe more effective hippocampus. This article is complex for the layperson. You basically put them in a maze that looked like it was about 1.5 meters long and about 3 inches wide. wide, where they scurry through. The subject, the rats, are those rats still alive? Do they have a long lifespan?
I would say like a couple years.
And I also read that everything was done in accordance with Massachusetts laws as far as dealing with animals.
They're very strict. NIH as well.
The subjects were implanted with a microdrive array containing 16 to 18 independently movable tetrodes. Now, I know you alluded to this a little bit ago, but what exactly is that in lay language? And it says in a skull screw, which they use as a ground.
I would say the technique is somewhat similar to what is done in humans if they need to record brain activity. So if someone has epilepsy and needs to undergo surgery to remove part of the brain, they need to record first, and they implant wires in the brain. Each wire can pick up a couple of neurons. But what a tetrode is four wires that are very close together. They're twisted and inserted into the brain. And it's a technique that allows you to record more neurons simultaneously because each neuron has a different sort of signature on each wire. So you can use four wires together as like an antenna to pick up many more neurons than you could with a single wire.
Okay.
So we just can put multiple of these tetrodes in the brain, and the screw is a reference. When you record electrical signals, you need to reference it to something. So we reference it to the skull.
You did at least 200 individual trials with these rats getting these sound cues, is that right?
Exactly. The animal just pokes his nose in this little device and hears a sound and then runs to the right or left depending on what sound is played and just keeps on doing this again and again. Every time it gets it right, it gets a nice little chocolate pellet for a reward. They love doing this. They just will keep on doing it till they get so full that the next day they're not even hungry.
That's what I was going to ask you about this nose poke. I didn't quite know what that meant. So they're actually doing the nose poke. You're not doing it.
Exactly. There's this like a little hole with a sensor, and when they put their nose into it, they cross a beam, and we can detect the beam with computer and know the time that the animal initiated the trial, and then everything runs after that.
So they're pretty smart then.
They are. They are smarter than you would anticipate. They can do a lot of things, yeah.
Amazing. Run through exactly what you were doing and what you were hoping to accomplish.
I mentioned before this idea of replay and that neurons in the hippocampus of rats are spatially selective. They're called place cells. Different neurons like different locations in the room. And you can get a sequence of neurons firing or active as the animal runs back and forth on a maze, and you see that same pattern occur later on. So the question is, if this replay is important for memory storage, then a hypothesis would be if you can manipulate that replay and make the animal replay more one event than another, that should influence memory storage. So you should remember better an event that is replayed more. So the question is whether we can manipulate this replay. And there was a study in humans that showed that if you play an auditory cue as part of the task, and then you play that auditory cue when the person is sleeping, they do better in the part of the task associated with the cue than another part of the task that's unassociated with the cue. So that gave us reason to test this out in rats, so we did sort of a simplified version of this task. When you work with rats, it has to be as simple as possible. So the animal hears one of two sounds. If it hears sound one, it will run to the right side of this maze. For the second sound, it will run to the left side of the maze. So it learns the task, it learns the association between the sound and the location, and when we watch these place cells in the hippocampus, we can see whether the animal is on the right side or the left side of the maze. And when it goes to sleep, we can see if it's replaying the right side or the left side of the maze. So it turns out if we play the sound that was telling the animal go to the right side of the maze, replay events when the animal is sleeping are more likely to also go to the right side of the maze. And likewise, if we play the sound telling the animal to go to the left side of the maze, the replay events are more likely to occur on the left side of the maze. You can interpret this as we're manipulating the replay using the sound, which you can interpret as manipulating what the animal is dreaming about.
That's the scary part, I guess, for a lot of people who read this. So basically what's happening is the little guys are doing their thing, they're doing their nose poke, and they're eating up all the chocolate stuff as much as they can, like you said, and they're exhausted, they're full, they're like we are on Thanksgiving, I guess.
That's right.
And so they go and crash, and then, of course, they still have the tetrodes in there, and you're monitoring what they're dreaming about, or how they're dreaming, and then while they're in that non-REM state, I guess because if they were in the REM state, it would just be too deep of a sleep, and then the external sound wouldn't be able to penetrate, is that correct?
REM sleep and non-REM sleep are different stages of sleep. You have replay or dreams in both. Most of the dreams you think about, like you're flying or weird stuff is happening, that's during REM sleep. And those dreams are longer in duration. And non-REM sleep are these very fragmented dreams that are very short. And it would be like run to the right, run to the left, run to the right, run to the left, something like that.
Right. That
is when the memory transfer is thought to occur. And REM sleep, it's still unclear what the function of that is. But non-REM are these fragmented dreams that typically you don't remember.
That's amazing that even today, in 2012, it's still unclear what the purpose is for REM sleep.
Yeah.
Wow.
It's amazing since so many across the animal kingdom you see non-REM and REM sleep, different proportions in different species, but yeah, it's not something you can avoid.
Wow.
Everyone has to do it.
How much we still have to learn, and there's people fighting and bickering over absolute nonsense. Thank you very much. Basically, what's happening is these little guys were, and like we said earlier, these rats have passed on because they don't have much of a lifespan, but these little guys were dreaming, and then you introduced this sound, and you had two sounds, which one was an ascending sound and one was a descending sound, I guess, something like that.
Right.
Then you introduced those sounds for, I think it was like maybe 5 or 10 seconds, and then when you introduced a sound that was associated with going to the left, if they were dreaming, for example, about the right side of the maze, then their dream would switch to them being on the left side. Is that right?
The dreams are very short in duration, so you can imagine over 10 seconds they could have these 3 or 4 mini dreams. They're only lasting maybe half a second or so. So there are these little bursts, so you can see right side, oh, this one's on the left side, and they're happening at random times. So we're not able to control when they happen. It's more that if a sound is played, the dreams that are happening afterwards are more likely to be on that side associated with the sound. It's more of a bias than we're just saying, okay, every single dream is going to be here. And I should point out that we're not manipulating these dreams in some arbitrary way. It's only related to what the animal has already experienced. So we can't say, oh, I wanted to dream about this room, and it's never been in that room.
You can't do it yet, but maybe one day.
Maybe. It's not like some government project to manipulate everyone's dreams. It's more to test how a recent experience gets transferred to long-term memory. If you can manipulate a process, it's a way of testing how well you understand how it works.
Right. And I just want to ask you something that might not be too related to this study, but you were talking about how these short-term dreams, or the non-REM dreams, are very rapid, like half a second. I've heard, I guess years ago, that when we dream, it seems like sometimes it encompasses a whole day, but I heard that dreams, like a regular dream, maybe a REM dream, only really last a few seconds. Is that true, or is that incorrect?
No, some of them can be a few seconds or longer. But I should add that when you record REM sleep dreams from the rats, they happen in the same time scale as the actual experience.
Ah, okay.
But non-REM sleep, the ones that we're recording in this study, happen 10 to 20 times faster. It's sped up.
Wow.
Your perception of time can also be altered. So it's not just the length of the dream, but also your perception of time. And then also how you remember it. Perception is a funny business.
Yeah, it reminds me of that movie, The Fifth Element. Remember when she was watching the monitors and she was sucking in all that information, all the news of the world, what war was about? That's what this reminded me of when you were talking about it, that these brains are just doing something like that in the non-REM state. Is it something similar to that?
Yeah, it could be. I think a lot of people have had the experience of playing a video game like Tetris or Quake, and then even you close your eyes, your brain is starting to replay these images, sometimes very, very rapidly.
Right. Yeah, that happened to me decades ago.
Yeah.
Okay, so in the discussion part, you say that we found that hippocampal replay activity can be manipulated by presenting a task-related auditory cue during sleep, such that the content of replay is biased toward the previous experience associated with that cue, and that's exactly what you said before. Right. And you say that these data support recent findings in human subjects that memory consolidation is improved by presenting task-related cues during non-REM sleep after a hippocampus-dependent memory task. And you touched on that also. So what this means then, if this is perfected, then there's a possibility that there can be some kind of process where during our non-REM sleep we could hear sound and somehow our memory could be more efficient.
Yes, exactly.
Because some people can remember everything. Could it be used, you think, for something like that, where somebody who is predisposed or pre-wired or born to not learn as fast than somebody who is, you might be able to level the playing field?
Exactly, and even more so, if playing an auditory cue is somehow affecting brain activity, and that brain activity is then influencing what memories are getting stored during dreaming, well, if we understand how that brain activity is getting altered, one of the brain, the hippocampus, cares about to decide, oh, I'm going to replay the right side versus the left side. Then there could be other therapies going beyond sound or olfactory cues that could influence learning much more or correct problems people have in learning and storing memories.
Yeah, great stuff. In the article, it says that the work was supported by a Merck award. I guess Merck is the big pharmaceutical company. And I know there's one in the United States. There's also one with the same name in Germany. So this is the one in the U.S., I guess.
Yeah, they're a sponsor for the Helen Hay Whitney Foundation, which gives a very nice postdoctoral fellowship award. So they're one of the sponsors of this.
Right. Yes, I did look that up online, and it looked like they give, well, about $50,000 for 3 years.
Right.
And also the Charles A. King Trust, they had given some money. Are they associated with Merck or not?
No, that's a separate foundation. It's a fellowship for 2 years, meant for, I guess, mid-level postdoc, so when you're in your 4th or 5th year.
And that's about the same money. They say $43,000 to $51,000.
NIH sets guidelines for what postdocs earn, so usually it's matched to that, roughly.
So the government decides how much you can make.
It's at a minimum.
And also the U.S. National Institutes of Health provided a grant, is that right?
Yes, Matt Wilson has a R01 grant. It's a large grant from NIH, and then I have a K99 grant, which is a transition grant between postdoc to faculty.
And how much did the NIH give?
I don't know the exact amount of Matt's grant.
Can it be segregated to this particular bit of research, or it can't?
No, I don't think it's itemized. When you write a grant, it's for multiple projects.
Okay, so if somebody read this or listened to this interview or read the articles, they might think that the U.S. government is funding research to engineer dreams.
Oh, no. The grant is on understanding how brain areas interact with each other to store memory and studying this during sleep. So there is no Department of Defense or any other agency. It's just basic science, curiosity how the brain works and how it can be used to solve disorders involving memory.
Right. So there's nothing nefarious about what you're doing at all.
Imagine someone has amnesia. They have some brain injury and the information is stored in one part of the brain but can't get to another part. Maybe if we understand how they communicate, we can have therapies to restore memories.
Right. This is amazing stuff. The brain is something that is so fascinating. You know how they talk about how the genome was mapped? How much have we mapped the brain? How much do we know about the brain?
Well, for some things, we know a lot, but often every time we have a discovery, we realize, oh, there's a whole other field we didn't know about. So we're definitely making progress, but there's plenty more to do. I won't be out of a job for my lifetime, that's for sure.
Well, that's a good thing. Is there much of a difference between, and of course we're talking the brain here, between the Long Evans rats, their brains, and human brains, as far as where this is concerned?
There are definitely some differences between rats and humans. The area we study, the hippocampus, is a preserved structure across all mammals, and so as far as we can tell, there'd be a lot of similarities. There are studies in other species, monkeys and bats, that are showing some differences, but in terms of the replay phenomena, that has been observed in humans. But it's very difficult to study in humans because to get these population of individual neurons that you can see these patterned activity, that's a very difficult thing to do in humans. So that's the reason we study it in rats.
Why is that difficult?
Just technically, we can implant a lot of wires in the brain of a normal rat. In humans, you're doing it in someone who has epilepsy. So that's a potential confound. You don't know how that affects your recordings. But you're recording from the brain, and the technology they use will take 2 weeks to search and get stable recordings. They have to do it within a couple hours. They have to go and record the neurons and go out. So we can use technology that I think gives us better stability and better isolation of these neurons. Plus, the animals are happy to run around for hours, day after day. That's what they do normally. And patients in a hospital, you're limited in the time you can record from them. So it's easier to have a more controlled setting, record from more neurons, and study things in detail.
But for example, you could theoretically, if I said, you know what, Dan, I want to let you use my brain to study and put those tetrodes in, I'll be fine, I can occupy, I'll just give me a book and a highlighter. Could we do that?
Not in the U.S. I think there's certain laws probably that prevent that. Because when you input a wire into the brain, there will be some small amount of damage. So it's not ethical to do it in a healthy subject, even if they volunteer. Right. It's not that you're going to go brain dead, but you don't want to undergo a procedure with risk. And plus, it's maybe not necessary. If we can see these signals in rats, we can infer what's happening in humans as long as we can draw connections between how the hippocampus works and other ways between humans and rats. So if it works in a similar fashion, then what we find in rats can be applied to humans.
Okay, and on the website of the Wilson Lab, they call this dream engineering. Would that be an appropriate term? If
you interpret replay as dreaming, then we are manipulating these dreams. You can engineer a dream based on an experience that's already happened, but not a novel dream.
And of course, the title of the article was Biasing the Content of Hippocampal Replay During Sleep. What precipitated the study? Was it something that Matt Wilson had on his plate, or was it something that you had on your plate, or did you guys get together and brainstorm?
I was interested in auditory-related projects because my background is, for my PhD, I was studying the region of the brain involved in pitch processing. And in this lab, a lot of people study the replay phenomena. So a study came out in humans showing that auditory cues can bias replay, just behavioral study, not neural recordings. Then that seemed like a great thing to pursue to understand what is the mechanism behind that finding. So we tried to replicate the study in rats, recording neural activity during replay to see if it can get biased.
Dr. Daniel Bendor, Dan, postdoctoral researcher in neuroscience at the Massachusetts Institute of Technology's Picower Institute for Learning and Memory's Wilson Lab. I want to thank you so much for the time you spent explaining all this to the listeners. It's a fascinating subject, and you really explained it very clearly, and I want to thank you and hope to talk to you in the future.
Thanks, Dave. Appreciate being on your show.